Now that we have our benches copied to each of our rows in the first column of the stadium, this video is going to focus on one method of coming up with the length of each of our rows so that we can drive our bench box, which is our box sot back here, we can drive the size X value such that each of our benches are properly sized on each given row. Now there are multiple ways that we can come up with the length of each of our rows. We're going to be exploring two of these different methods over the next two videos. In this video, we're going to be looking at a more complex way of calculating that distance. In the next video, we're going to look at a simplified method. Now, why are we showing two different ways, and one of them being a more complicated method? Well, in this particular case, we happen to have geometry information that we can use to easily calculate the length. But there may be times that you're wanting to distribute something around a polygon type shape, and you may not have geometry information to query to generate length information, because length information is what we're looking for right now. So knowing two different methods will be good. But to be honest, I have another motive, and that is to demonstrate that one can easily jump on the internet, find a formula that will help derive a particular value that you are in search for, and take that formula and easily plug it into a parameter in Houdini to generate the number you're looking for. This makes the internet, once again, a very powerful tool, as you'll find pretty much every formula in existence on the internet.
Yeah, so when you're working in Houdini, don't just limit yourself to 3D related text. Get out there, look at maths formulae, be they on the internet, be they in books in your local library. Just get out there, because mathematics is at the core of 3D applications, and you can apply mathematics to so many different situations.
Exactly. So what I'd like to do for starters is jump over here to the whiteboard, bring up, let me see how I want to do this. I'll go ahead and bring up another blank sheet, and let's start working right here. So first of all, just to give everybody an idea of what we're doing, let me go ahead and create a top view of our stadium. I do that every time. That's better. So, Steve, looking at this amazing drawing, how many columns do we have?
We have 3 columns.
Fantastic. So we have 3 columns. Let's stipulate that we have 2 rows. Again, this is a top-down view. On the 2 rows, we know that we've got a point copied there and there, or a point placed there and there. And these points will be used for us to copy our benches to. But right now, our benches, while they have been rotated and copied to the right spot, they're all the same length, and that is a bit of a problem. We need for them to be sized appropriately on each row, and each row is going to have a different length. Now, we know that when we first started out, we had a point here and here with the original profile curve that we created, and we saw that we were quite easily able to calculate with good old 180 over our number of columns, the angle so that we could put our points right here. Okay, that's good. With this information, we're armed with everything we need to calculate the length, if you think about it. The information generated by calculating the distance between those 2 points acts as the length describing how long that row is. And you'll notice that as we work our way up, each row is going to get progressively larger. This is the easy method. Take one point, take the other point, let's find the distance between the two. Woohoo! We've got the information, let's use it. And we're going to explore how to use that in the next video. Now, I've already given you a couple of reasons why we're showing you 2 ways. A third reason is because we're going to get to use some pretty cool nodes as well. Not necessarily pretty cool nodes. We're just going to get to use a very unique way of dealing with numbers within a network in the next example. So it's going to be a very simple example, but how we're working with the nodes is going to be really cool. And we'll see more of that in a minute. In this example, we don't have to have any new nodes added into our network. All we need to do is come up with some information in a very simple expression. Okay, not a very simple expression. Yeah. It's a little involved.
Whereas in the simpler case where we're just finding the distance, we will need some new nodes in order to implement that.
Precisely. So you guys are going to get a lot out of the lesson, out of the two different lessons. So in this particular case, how are we going to go about calculating our length? Well, first of all, we need to figure out what kind of formula we'll need and what information we're looking to achieve. Well, the information we're looking to achieve is a length. Basically, how long it is from here all the way down to there. Well, if we were to take a look at our revolved stadium as a whole, we could say, especially here looking at a top view, it makes it a lot easier to see. We're dealing with a polygon. And this is what is known as a regular polygon. And what makes it classified as a regular polygon is because of the revolve, all of our lengths of each side all the way around are the exact same length. Okay, so if looking at this top down, I just see polygon, another polygon, if we want to look at it that way, and another polygon on the outside. And we're wanting to calculate the length on these rows. So, if you look at it like that, you could say that these guys define polygons, right?
And it almost might be easier to visualize if you extend it through 360.
Yeah, I knew where you were going.
Sweet.
So if we do this right here, now you can truly see the polygon and see that it's still horribly drawn.
But we're dealing with a hexagon that has various different radii.
Exactly. So now we know that we're only dealing with 180 degrees. That's what we set our end angle to on the revolve. But if we look at all 360 degrees, we have a polygon. Now, Steve has jumped online, went over to Google, typed in formulas for regular polygons, and we've come up with this page right there. Actually, there's a lot of different pages where you can find these formulas on. But this case, we happen to be on a website called mathforum.org, and you can see the address up here. So if you'd like to go there, go ahead. Or you can just search for regular polygon formulas. Now, it's very easy to find the formula as long as you know what it is you're looking for. In our case, we know we're looking for a length. And I say that by simplifying this stadium into an honest-to-heavens polygon.
Yeah, so when you're looking through the different formulae, you need to look for what we're trying to find, and also have a look to see what pieces of information we know that we can calculate. As long as you only have that one unknown,
But we start with knowing what's the piece of information we want to know. And in this case, what's the piece of information we want to know? We want to know the length of a side.
Exactly.
So we just want to know how long one side is. And since this is a regular polygon, every single one of our sides are the exact same length, and all of our angles on the inside are the exact same angle all the way around. Okay, and that's what makes it a regular polygon. So I know I want length. Now, what kind of information do I have about the polygon? I actually have a lot of information. We know how far it is from here to here, so it kind of looks like a radius to me. We also know that we're able to calculate our angle right here. We've already done it with 180 since we were only dealing with half of it over the number of columns. So we can come up with that information. So with all this information, I'm sure we can find a formula that's going to give us a length. So let's go ahead and come back over here and take a look at all of the different formulas. So we know that we're looking for a length. So number of sides, all of our sides are equal in length, and that is going to be represented with A. Okay? Well, let's see. Do they provide any formulas that solve for A? Well, starting right here, we begin with our formulas. And looking all the way down, so beta, alpha, no, P, K, looking, R, little r, A. Oh, A. What did we just, hey, I didn't mean to select all that. What did A? What is A? A is once again the length of one of the sides. So all of the sides are going to be equal to A. So excellent. We have a formula for solving for the length. So wait a minute. Equals this formula, which equals this formula. All right, what's the difference between the two? Let's look a little closer. Well, we're using tan in this one, sine in this one. That's irrelevant. Looking a little bit closer. Big difference. We're using a little r over there, and we're using a capital R there. Well, let's see what the r's are. Okay, so starting back at the top, working our way down, we know what A is now. We can find beta, alpha, P, K, R. There's a capital R, and there is a lowercase r. By the way, I just don't want anyone to assume that I'm being sarcastic as I'm working my way through this. I'm just trying to talk out loud about how one could go about looking at a page like this and start coming up with each of these different values.
Because when you realize that you need to calculate the length of a side in a regular polygon, you're not going to be able to pluck a formula out your head.
No.
You need to...
Well, unless you're Steve.
Well, even I had to look this up.
They didn't have to know that, Steve.
So it's all about looking for formulae that have the unknown that you're trying to find, and that equal to a series of pieces of information that you know you can find.
But then as you look at the series of information, now being able to break that information down into numbers that you can plug in.
Exactly.
But here we've got a little r and a big R, and I don't know what that means. So I'm once again starting at the top of the page, working my way down, and we need to figure out what is the difference between little r and big R.
So we can find out which of these we calculate.
Which formula do we need to use? All right, so working our way down, we just stumbled on a large R and a small r. Radius of a circumscribed circle and the radius of an inscribed circle. Well, what's the difference? Well, just in case anyone has forgotten from their days with simple geometry, let's go ahead and jump back over here and take a look at inscribed and circumscribed. Basically, if we were to take a circle and take our polygon, and I'm just going to use a very simple polygon to represent this instead of drawing out all of the sides of the guy up above. An inscribed circle would be a circle that would touch, we're all going to pretend I just drew a perfect circle. It is going to touch all of the edges of our polygon. Okay? So again, that would be a circle. Here we go with another horrible hexagon. That would sit inside this guy. And this is an inscribed. Okay, now circumscribed is going to be, once again, we'll take our polygon. In my case, I'm just going to draw out a very simple four-sided polygon because that's going to be easy to draw. And we're going to draw a circle on the outside, but you'll note that the circle goes through all of our corners. Okay, where we attach all of our edges. This is a circumscribed circle.
I'm going to have to be really picky and ask that you throw the D on inscribed as well.
All right. I knew you was going to do that.
Much better.
You kept winking at me. I thought there was something that you wanted to say, Steve, other than, put the D on the end. Okay, so now we have...
Now that I'm uncomfortable.
Hey, I said inscribed, okay? Sometimes I get carried away with my drawings and leave letters out. It happens, but we all know what I'm talking about. So jumping back over here with Ask Dr. Math, we have our circumscribed circle and our inscribed circle. And look at this. In this particular case, the radius of a circumscribed circle would be the capital R, and the radius of an inscribed circle would be our lowercase r. Well, let's see which one of these circles are going to apply based off the information we have. Jumping back over to the whiteboard, we know that we can calculate from right here all the way out to the edge. Well, let me start right here. Because remember the inner radius? We use the inner radius to push out. So we can calculate to here, and then we know how far it is out because of our unit profile curve that we created. So we can calculate all of this guy all the way out. So I'm going to calculate them all the way out to the end. That means if we were to draw a circle around here on the end, look where the circle's going through. Again, and this is only happening because all of our inner angles are the same and all of our lengths are the same. And because of that, the circle is going to travel through all of the points of our polygon. Beautiful. Okay? So, with that being the case, jumping back over here, that happened to be a circumscribed circle, so we're going to be using the capital R. Because of this piece of information, we now know which of the two formulas we can use to give us A. Well, at least we know that we're on the right track.
Yeah, and exactly, because all regular polygons will have the inscribed and a circumscribed circle.
Right. Well, you can always put a circle on the inside or on the outside.
But we can see that our circumscribed circle is so easy to calculate because we know the distances and because we've been working with specific distances using units for each row and the likes.
And so basically we have inner radius, And then we have our 1 unit profile curve that's going over. And we know that half of that was the distance where we copied our bleachers to. So we have our inner distance plus 0.5, and that gives me the distance out to the very first bleacher that we're going to be placing.
Whereas if we tried to calculate the inscribed circle, we'd have a lot more to do to get there.
It would be a bit more complicated.
Exactly.
That's for sure. So we've got this guy right here. So 2r sine of alpha over 2. All right, what's alpha? All right, so alpha is something new. Coming back up here and working our way down. Let's see, no alpha, beta. Alpha. Central angle subtending one side. That's alpha. Wow, this guy is actually very easy to calculate.
Yeah.
We've already done it. Let's go ahead and jump back over here and take a look. Oh, wow, we've already got it drawn out right there.
Yeah, saying the central angle subtending one side is just a mathematical way of saying the angle that's going to define just one of our segments when we did that revolve. And we've already calculated this.
So if we were to take and look at the entire polygon. So now I'm looking at that's awful. All 360 degrees. So we were to divide this guy up, right? Very easy to calculate this, and alpha is basically equal to, and once again back over to the formula, alpha is going to be equal to, coming down further, so here we are, alpha is equal to 2 pi over n radians, which is equal to 360 degrees over n. N, what's n? How many of these sides do we have? Our sides, okay? Well, 360 over n, we know how many sides we have. We have number of columns that tells us how many sides we have. So we have that information. So 360 over n. So let's go ahead and jump back over here to the whiteboard.
And of course, we do have to remember that the regular polygon does extend through 360 degrees and not just the 180 that we're creating.
So alpha is going to be equal to 360 over n. All right. Let's take a look at this now. 360, using some of the numbers we have available for us now, we have num columns, so I'll just put num column, but we're using 360, so we're dealing with a polygon. This guy goes all the way around. Our benches, our stadium, is only 180 degrees, so we need to go ahead and bring it all the way around as far as the maths are concerned. And to do that, can't we just take our number of columns and multiply that by 2. So if we've got 3 times 2, 4, 5, 6. So
fantastic.
Times 2. So, well, we're using multiplication, so now we can come in here and simplify. So we can get rid of the 2. 2 is going to go into 360, 180 degrees. So alpha is going to end up equal to 180 over the number of columns.
And that's a very familiar expression to us.
We've already
used him already.
Recall in the last video we used that to get this information right here so that we could copy the points to right there. So we've already seen it.
We've already seen them.
And now you've seen why we use that formula, which is fantastic. Okay, so we've got a piece of the puzzle. So let's go ahead and jump back over. So as we work our way down, we now have alpha, so we can easily use sine. So sine's an expression function that's built in. So sine of alpha over 2, so we've got that. In fact, we could even simplify that even more with it being over 2. So let's multiply it by 1/2, and that'll end up being like, 90 over a number of columns, which we'll talk more about that in a second. R. We need our radius now. And once we get our radius, we just multiply 2 by our radius, by the sine of alpha over 2, and we have the information we need for each row, because each row is a changing value, so we're going to have to deal with that.
Each row is going to have a change in radius, which is why each row is going to have a change in length.
Exactly. So let's go ahead and jump back over to the whiteboard real quick, and let's see, how much room do I have here? I got a little bit of room. Let's play. So what is our radius equal to? So figuring out the large R. So we know that since this is a circumscribed circle, that our radius is going to run out to one of our points, and we can calculate all the way out to a point right there. How far, as I said earlier, we can calculate to each of these rows and even to the midsection of each row by using the inner radius, which is a parameter that we set up on our asset that we use to push that profile curve over. So R, we know we can just start right out with saying, well, R is going to be equal to at least the inner radius. So now that takes us from a center point out to where our first row begins. Okay, well, we can calculate yet more information. Where do we need to calculate the length at? So how far is it out really to the circle, the radius? How far does it really go? It doesn't go to right here. It needs to go to right here. It needs to go into the center point of each of our rows.
Yeah, because that's where we've copied our benches to, so that's the polygon the benches are going to define.
So that's the length we need to know, because we need to make sure that our benches are less than that length.
Exactly.
Okay? So otherwise we're going to have some nastiness take place. So we're calculating to right here. Well, we know this information as well. This was, if you remember, in Z we just went back negatively 0.5, since this is our unit profile curve, which went back all the way 1 unit. So if we just take our inner radius and add to that 0.5, that now has us calculating a radius that goes all the way out to right here. And that's brilliant. That's what we need. But there's more. Recall, we could have more than one row. If we only had one row, we could stop right now. But the moment we have a second row, this guy goes up and over, and now we need to calculate to right here. Once we have a third row, now we need to calculate to right here. Fortunately, through stamping on a copy, we can take information and we can send it back up into a network, so that as the network is processing information, it can kind of see into the future and make decisions on where it's going to end up being in the future. And that's really nice. One of the things we're going to do here is we're going to take a look at what point are we copying to. Because if you recall, we isolated our bench template points, right? So we have point, point, point. And remember, when dealing with a series of points that's running through a network, these guys are 0, 1, 2, they're numbered. Okay? So we can take this point number and we can stamp that back up, all the way back up to the expression that we're starting to put together on our box to control the size. Steve, are you starting to feel this video?
I'm thinking I know where this is all going.
Excellent. I just want to make sure you're feeling it. You got a big grin on your face over there. So we can use this information, stamp back up onto the box in the expression to offset our radius, or to extend our radius, so that we have the right radius for the right row that we're currently working on. So watch how easy this is. All I need to do is get row number here. So what row number? I'll just put row num.
Exactly.
And where are we going to get this information? On the copy that we've already set up, that copied all of our benches to each of the rows. We'll just simply set up for stamps with a variable. We'll call the variable something like, I don't know, row num, and the value of it will be the local $PT. Basically, what point number are we currently copying our source geometry to? That's simple. So that's going to send us back up a 1, a 2, a 3, but it's going to start at 0, so here's the beauty. The very first number that gets stamped back up here, we're going to take our inner radius, so that's going to push us out this far, to the start of the profile curve. Then we're going to add to that 0.05, so that pushes us right here. And then we're going to add to that our row number, which stamped back up, the very first one is 0, so we don't add anything to it.
Fantastic.
Puts us right where we want it. The second time we come through, we stamp back up the number 1. Well, look at this. 0.5, 0.5. Oh, we're right here. That's the beauty of having this unit profile curve where everything is based on 1.
Yeah, exactly. When we first designed this curve, we said building everything with units, so we go up by 1 and back by 1 each time, was going to make some of the maths a lot easier. Mm-hmm. And we saw that just when we were copying the individual bits of the profile, we could go up 1, back 1 to create each of the steps. Mm-hmm. Well, here's another instance where having that basic numbering system is making life really easy for us.
So if we were to come down, we know that we're calculating for length. And length was equal, and remember length was A, it is equal to 2 times capital R. So jumping back over here, so 2R. So let's just start breaking this guy down, because we've already seen we've got R and we've got alpha. So we've got everything we need for this guy. So coming back over here, so we'll have 2 times, and instead of writing the capital R, we've already solved for it. So let's go ahead and just throw this guy in here. I'm going to use parentheses because of order of precedence, and we are using some addition in here. So we don't want to just take 2 and multiply it by inner radius and then start adding stuff to it.
That would be bad.
Not good. So we'll take inner radius. Plus 0.5 plus our row num. Information that we are, that's an M, information that we're receiving back up from the copy. But there's more. Coming back
so that's
over
how
here.
2 times R.
That's 2 times R times the sine of alpha over 2. Jumping back over here. So times the sine of alpha. Wait, do we have alpha?
Yes,
we sure do. 180 over num columns.
And since we're dividing that by 2, it's like multiplying it by a half.
By 1/2. Multiply by 1/2.
Which
and we
can cancel down.
Do you want to do this lesson? So we can cancel down. 2 is going to go into 180 90 times.
Nice.
So now we have 90 over num col. So make sure everybody take that in, okay? Because Steve was over here interrupting me. I love you, Steve. It's all good. So basically we have 90 over num col. So let's go ahead and just clean this up now that everyone sees where that number came from. There you go.
Sweet.
I'm looking at every single thing over here except for length, and this is what we're solving for. We have the number 2. It's a constant. We have this guy. This information is being stamped back up from the copy. We have our number of columns from our asset parameter. That's everything we need to pull this off.
Yep.
And all we need to do back over here inside of Houdini is take that information and apply it to our size on our box, and that is going to give us a different size for each of our benches. So that's pretty much all we need to do.
Yeah, now we've got all the maths theory down and we've simplified things. It's going to be incredibly easy in Houdini. We stamp back one parameter and then we set another parameter equal to an expression and then we're done.
And no new nodes or nothing.
No new nodes or anything.
And while if we wouldn't have explained this, it may have looked a bit intimidating.
For
those that have not yet had maths that deal with geometric shapes.
Yeah, exactly.
But there's nothing complicated about the maths that we've used here at all.
Take everything step by step, simplify things down where you can, look at everything logically. We know we could find a radius and we saw how we can break that down. If you take everything nice and slow, maths doesn't need to be daunting at all. And
the big thing I would like for everyone to take away from this lesson is that don't be shy to get on the internet if you know you're looking for, I want to calculate the distance of this, or I want to calculate the velocity of that. Well, what kind of information do you have? Jump online, type it into Google. You'd be surprised. The internet can be very helpful in giving you formulas. You don't have to have thousands of formulas memorized. You just need to know how to be resourceful and get to the formulas. And then we're showing you here how you can then carefully break a formula down and use it. So, Steve, with that, I think it's pretty much time for us to jump over into Houdini and put this guy together.
Alright, so let's jump over into Houdini and implement this guy.
Where all of our viewers are going to think, wow, you just did about half an hour for a 3-minute.
It's going to be pretty crazy. We jump over into Houdini, it's going to go very quickly. But without the explanation, without simplifying things down, things would be a lot more complicated.
For sure. Alright, let's do it.
Fantastic. So, jump over into Houdini, and the first thing I'm going to do is we need that row number piece of information. So let's deal with stamping him up from our copy. Which copy am I talking about? This copy here, where we copy our benches to each of the points we've created for them. Each point is going to have a number coming in, and that number is going to be zero-based, as we've seen on the whiteboard. So 0, 1, 2, 3, and 4.
And we want to send that number back up in time so that as we are calculating that expression, that piece of geometry is going to know in the future, when I get run through the copy, I'm going to be located on the first row or the second row.
Exactly.
And it'll take that information into account.
And this is really easy to do. We've got the point number that we're copying to, and we've got that available as a local variable on our copy. So I'm going to bring the visibility down to the copy, come over to our stamp folder, check stamp input so that we do invoke stamping, and let's create a row number variable. So row number, what value are we going to stamp back? That local variable that's our point number, and that is $PT. So we're stamping back $PT, which means for each copy of our bench, this guy's going to have a different value.
Yeah, the
0,
copy
1.
itself knows, all right, I am copying the source geometry to the first point, so $PT is 0.
Exactly, so each time we copy it, we'll get recooked the network creating our bench. It will replace this stamp with a new value, 0, 1, 2, 3, and so we can recalculate the expression that we've seen here.
That's right.
Let's get an arrow. There we go.
Right.
So we've seen that we need that expression to control our size in X. I'm going to turn off points and
Yeah.
That was nice. So I'm going to bring up the expression editor. I'm even going to make him full screen. So that was on size X for our box. So what does our expression look like? Our expression looks like 2 times our inner radius plus 0.5 plus row number. So let's deal with this bit first, and then we'll come in and deal with the end of the expression.
Sounds great.
So 2 times our inner radius. Well, our inner radius is just a parameter up on our asset. So we can grab our inner radius from our asset. We then add 0.5 to that. 0.5 is just a constant, so that's nice and easy. And we've just stamped back the row number that we were after, so we can grab him by
we have to use the stamp.
Using the stamp expression. We need to specify which copy we're stamping from, and that was our copy benches 4 rows. We have to specify what we called that stamped parameter. We called that stamped parameter row number. And we have to give a default value. Well, use a default value of 0.
Just in case anything goes wrong.
Yeah, if it explodes, we're going to get the value of 0 come in.
So we'll definitely know something's wrong because it's going to be 0. We're
exactly.
not going to have much of a bench.
So we've got, I've closed off this bracket, so we have 2 times all of this, because again,
so there's 2 times R.
Yeah, because we've got additions, we want to make sure all of this is multiplied.
So yeah, that's basically your radius.
Fantastic. So we've got our 2 times our radius, and now we just need times sine of 90 over our number of columns. Well, that's nice and easy. Times sine is available as an expression function in Houdini, and it just needs to take in a value for the angle, and the angle we've seen is 90 divided by our number of columns. Our number of columns is available as a parameter up on our asset. Close off our sine expression, and with that, that's literally everything we need. So we've got 2 times inner radius plus 0.5 plus row number times sine of 90 over number of columns. 2 times inner radius plus 0.5 plus row number times sine of 90 over number of columns. Fantastic. Yep. So let's accept that.
Look at that.
Look at that. We have a slight issue, however.
Yeah, just a little bit. And this is what I was talking about when I said there'd be some nastiness if we left it the entire length.
Because we've just calculated the entire length. If we were to then copy that round, they're going to intersect.
Yep.
So let's just take a percentage of that
Go ahead and
length.
take a minute and work out the math to angle our benches so that they just fit flush. I'm just kidding.
You just blew my mind.
Oh, that'd be fun. For those of you watching, that's a nice little challenge. What if you wanted to leave it the length, but you wanted to shear your angles in such a way that the benches fit all the way around?
It's doable.
It's very doable,
because we just need to calculate our current length and how that varies with the length of this point and this point.
Exactly.
So we reuse the regular polygon expression we've already done. And once you have the 2 lengths, you can then work out a scale factor between them and scale the 2 guys up. We're not going to do that on video because
I just gave it to him as a challenge, but now you just gave him an answer.
I gave him part of the answer. The hard bit is...
No, you gave him the answer. Okay, so you didn't give him the full answer.
It's a hint.
For those of you watching, you've just got a very nice hint. But yeah, work that out.
Cool.
It really isn't difficult. It's all about determining a scale factor for one of your sides.
Exactly.
Okay.
Sweet. So we don't want to take all of our inner radius. I'm going to say let's take 0.75, so 75% of our radius, of our entire length.
Yeah.
And
so that our benches will always occupy 75% of the row.
Exactly. So we can either do this by saying 0.75 times our existing expression. If we accept that, we'll see that they now take 75% of the row. But we got 0.75, that's a constant value, times 2. 2 is a constant value. So we could just multiply these together and simplify. So we can take all of this and replace it with 1.5. We go no change in the end result, but we've simplified our expression slightly. But yeah, nice and easy. Once we've got all of this simplified down to a single expression, it's nice and easy to
be honest with you, I'm just looking at it myself, that for those that were just listening to the challenge, that there were a few of them that thought to themselves, I'm not going to use the math and come up with a scale factor for one of the sides of the bench. I'm just going to come up with a new system that allows me to use revolve again with a different curve that's going to make the whole thing work.
And that would work fantastically.
Yes, it would. But anyways, it's Houdini, and there's probably 1,000 ways to do any one given thing.
Yeah, and we've seen we're going to have 2 ways to calculate the length, because we're about to turn around and use a completely different approach.
Yep, a different, easier. It is easier.
It is easier in terms of the maths.
But there's the overhead of another node that's in there.
Yeah, it's all about personal preference, because one person may find one approach easier, another person may find, because I personally find the math approach it talks to me, it works in my head.
I totally understand that.
So
in regards to you and math.
Yeah.
So all right, so with that's everything that we wanted to accomplish in this video.
Fantastic.
We'll see you back in the next video where we will take a look at another approach to solving the length of each of our rows. Thanks a lot, guys.